Vale. Bueno, pues buenos días de nuevo. Hoy tenemos a Margherita Giustini como ponente de nuestro seminario. Y para presentar a Margherita, pues Margherita hizo su doctorado en Bolonia en el año 2011 y después de realizar el doctorado se trasladó a Baltimore, en donde hizo una estancia de 6 meses. Después de Baltimore pasó a ser un Research Fellow en la ESA durante 2 años y posteriormente se incorporó al Instituto de Investigación Espacial holandés, a SRAM, durante 3 años, para en el 2018 empezar a trabajar en el CAP y desde el 2019 pues, tiene un contrato de atracción de talento de la Comunidad de Madrid y lo está desarrollando en el CAP también. Así que muchas gracias, Margherita, por ofrecerte voluntaria a darnos esta charla y cuando quieras.
Pues muchas gracias a ti, Jasmine. And okay, I'll switch to English for this talk. And it's a great pleasure to be here, to even remotely, but telling you this story. This quite amazing story of the discovery of a new cosmic phenomenon detected in the nuclei of distant galaxies and associated to the flow of matter very close to the supermassive black holes which are in their center. And I could not be here today telling you the story without Giovanni Minuti, who is the discoverer of quasi-periodic eruptions, QPs, and also Richard Saxon from the European Space Agency, who is the discoverer of the X-ray activity of the galaxy GSM-069 itself. The details about the work that we have been doing in the last few months about this subject can be found in these 2 articles, one published by Giovanni last year in Nature and the last one published a few months ago in Astronomy and Astrophysics. Now, during this talk, I will try to keep things basic, things easy. So the idea is to telling you the story in this way. To start, introducing you to the world of galaxies and their supermassive black holes, and then explaining you a little bit how can we observe these cosmic sources. And this should allow me to introduce you the discovery of X-ray quasi-periodic eruption in a meaningful way. So galaxies. Galaxies can be seen as the fundamental building blocks of the large-scale structure of the universe. In this image, this is an optical image of the outskirts of the Coma cluster of galaxies. So the Coma cluster is one of the many clusters of galaxies of our universe, and it's a collection of hundreds, thousands of galaxies, each one with its own size, its own shape. Galaxies usually come in 2 different shapes. Here I list actually 4. So we have spiral galaxies, like the galaxy where we live in, the Milky Way. These are galaxies which usually contain hundreds of billions of stars. So galaxies are a collection of an incredible number of stars, a very, very large number of stars. We usually count the stars of galaxies in units of hundreds of billions. So a few hundreds of billion stars for a typical spiral galaxy, a much smaller number of galaxies for the so-called dwarf galaxies, and more or less the same amount of galaxy of a spiral for the irregular galaxies, which are shown here in the middle, which are like a indefinite, not very definite shape. And finally, the elliptical galaxies, the giant galaxies that we can find in our universe, which can contain up to hundreds of billions of stars. Now, we live in a galaxy, so a galaxy is our cosmic home. We call this galaxy the Milky Way. Why? Because when we look at the optical, at the night sky, we can see, if the sky is dark enough, a very light band of light in the sky, which to the ancient humans resembled somehow milk. And so they called this like the Milky Way, the road made of milk. And now we know that these are actually hundreds of billions of stars, stars like our sun, that compose this galaxy in the form of a spiral structure. Now, we cannot see the galaxy as a whole because we live within the galaxy. So we actually live in one spiral arm. So this is an artistic view of the whole structure of our galaxy. You can see a bright bar in the center, and then the blue arrow points the location of our solar system. So our star, the sun, is located in between two spiral arms of our galaxy. And from our cosmic position, when we look at the night sky, we basically observe the inner spiral arm, which is toward the galactic center from our position. But let's take a look toward the center of our galaxy, thanks to the European Southern Observatory video made of real images. So let's start zooming in what we call the Milky Way. Let's approach the center of our galaxy. The center of our galaxy is about 27,000 light years from Earth. Our galaxy is very wide. So let's pierce toward the center of the galaxy. You can see a huge number of stars. These are real optical images with increasing resolution and exposure. And we are starting approaching the very crowded area where massive clusters are also present. And we are approaching more and more the center of the galaxy, where a lot of dust obscures the direct view of the galactic center. So we need to rely on infrared observations. And these are observations in the infrared of stars very close to the galactic center. So we are looking at star 27,000 light years away, which is amazing. And following the orbits of the stars, humans were able to pinpoint the location of a very massive object, an object that we call Sagittarius A star. And we know today that it must be a black hole, an actually supermassive black hole with a mass of 3 to 4 million times the mass of our star, the sun. So let's come back to our cosmic home. So let's zoom out. So what happens? By measuring the velocity of the stars close to the galactic center, we can derive the mass which is enclosed inside these orbits. And it results that in such a small volume, a huge amount of mass, again, 3 to 4 million times the solar mass, is concentrated in the center of our galaxy. So there is a supermassive black hole in the center of our galaxy. We know this since about 20 years now. And for example, in the past 2 years, thanks to the realization of the presence of this incredible cosmic source in the center of our galaxy, we were able, as astronomers, to measure with a lot of precision deviations of an orbit of a star which passes very, very close to this central supermassive black hole. We were able to measure distortions from Newtonian gravitation in terms of gravitational redshift. So it's something that general relativity of Einstein predicted. So as soon as the stars came close enough to the black hole at the center of our galaxy, not only its orbit deviated a little bit, but its color also changed and became redder. So I think personally, which is that is really amazing that we are able these days to measure this kind of event in the center of our galaxy, where we realize there is a supermassive black hole. Now, the supermassive black hole at the center of our galaxy is dark, is silent, is not eating very much. What are black holes? Black holes are the most compact objects that we know in our universe, that we can imagine in our universe. So these are regions of the space-time where a huge amount of matter is compressed in a very tiny volume. And so the gravitational pull very close to the black hole is virtually infinite. And it's so high, it's so large that the black hole defines, you can imagine the black hole like a distortion of the space-time with an infinite density at its center. And there is a surface, which is called the event horizon, which defines the location of space-time where the gravitational pull of this matter, which is inside, is so strong that not even light can escape. And so time is frozen into the event horizon of a black hole, and the photon, any photon, is just frozen there. So by definition, we cannot observe black holes. And in a minute, I will tell you what we actually observe then. So black holes are fascinating objects, and they are relatively simple. So they can be described completely only by using three physical properties. So their mass, their spin, so how fast they rotate, and their electrical charge. And in our universe, the black holes have no charge, so have a neutral net electric charge, so we can forget about charge. And the spin is also very difficult to measure, and for the purpose of this talk, we can forget about the black hole spin. And this means that we can characterize black holes just by their mass. So how mass did they eat before becoming black holes? Now, the mass of the black hole defines how big it is, simply. So its radius, which is called the Schwarzschild radius, scales linearly with the mass. So this means that the more massive is a black hole, the larger it is. For example, if you take our star, the sun, and you compress it to the size of the city center of Madrid, for example, so a size of more or less 3 kilometers, you would get a black hole. So you would make the sun so dense that it would collapse into a black hole. If you would do the same game with our planet, Earth, you would need to squeeze the planet, for example, between your fingers up to more or less 1 centimeter, and you would get a black hole. For our moon, a black hole moon would be barely visible by human eye, would be much smaller than a millimeter. But cosmic black holes can be huge. So the supermassive black holes, which are hosted in the center of galaxies, they can be extremely large because they can be extremely massive. So they can be as large as the distance between the Earth and the Sun. And in the most extreme cases, they can be as large as the whole solar system. So very big things. Again, how do we observe black holes if by definition they don't emit any light? On the contrary, they capture light and they don't allow photons to escape. So what happens is that contrary to the black hole, which is at the center of our galaxy, which, as I said, is not eating that much, most of the black holes that we know are active. So if you look up at the night sky with optical light, you can typically observe stars, fine, like our sun. So the luminosity of a star is more or less like a solar luminosity, 10 to the 33 erg per second or so. You can also observe galaxies, as I just told you. So collections, huge collections of stars, of hundreds of billions of stars, whose total luminosity is more or less comparable to the sum of the luminosities of the individual stars. And then you can observe quasi-stellar objects, also called QSOs, because they look like stars. So they are point sources in optical light and really look like stars, but they are much more luminous. Not only they are much more luminous than any star, they are much more luminous than any galaxy known. And in fact, this image, this image that you can see of the quasi-stellar object, if you block the center of the aperture of your telescope, you can recover the following image on the right. So this is the same cosmic object, but on the right, the central part of the detector of the telescope was blocked. And so you can see that the central light is off and a very faint galaxy can be seen below this very, very bright cosmic source. So what astronomers called quasi-stellar objects, they realized they were active galactic nuclei. So some activity, very strong activity, able to generate a huge amount of luminosity in the very center of distant galaxies. what are these supermassive black holes? So the only mechanism that we know able to produce this huge amount of electromagnetic radiation is accretion of matter onto supermassive black holes. With supermassive, we mean usually something between millions and billions of times the mass of our sun. And the accretion luminosity is given by how much the black hole is, so m dot, so the rate of increase of the mass of the black hole, by the square of the speed of light, c square, and multiplied by the accretion efficiency, eta. Now, the accretion efficiency is extremely high. Like, you can compare this value that I list here, like from 6% in the case of a static black hole, up to 40% in the case of a maximally rotating black hole. So this value of efficiency of conversion of gravitational energy into electromagnetic radiation is really huge. It's more than 10 times larger than the efficiency of nuclear fusion. So what does it mean? This means that if you, for example, if you throw just one solar mass per year, one star, you feed a black hole with one star per year, you can easily obtain a luminosity of the order of 10 to the 45 ergs per second, which is comparable or much greater in many cases of the luminosity of an entire galaxy. So by just throwing one star into the center of a galaxy with a massive black hole, you can obtain a luminosity that exceeds the whole galaxy itself. It's something amazing. Are black holes active black hole commons? Yes. This is a collection of images of galaxies of the local universe. So you can see in many cases below, and then at the center, a very bright nuclear source of light. So all actively accreting black holes. So black holes in a few decades went from being some abstract concept, mathematical concept in the human mind, to be some fundamental cosmic actors. So we realized that we need to understand the physics of black holes if we want to understand the physics of the evolution of the large-scale structure of the universe. And why? Not only because there is a black hole at the center of the galaxy, as I told you, but because there are also strong evidences that this central black hole and the galaxy itself can have a profound relationship within each other. So we speak today, as astronomers, we speak today of cosmic feedback. So what was realized was a couple of decades ago is that the properties of the central supermassive black hole and the properties of the galactic bulge, so the central portion of the galaxy, correlate quite tightly within each other. So graphics, you can see on the vertical axis a measure of the mass of the central black hole of a galaxy with 1 million solar masses in the bottom and 10 billions in the top. And on the horizontal axis, you can see in the left plot the luminosity of the galaxy, of the galactic bulge, and in the right plot, the velocity of the stars which are in this galactic bulge. And from the two graphics, it's clear that these properties correlate with each other. How to say? To more massive black holes correspond more luminous galactic bulges and faster stars which go around in the galaxy. And this is surprising. This is surprising mainly because the dimensions, we are comparing two kind of cosmic objects with extremely different dimensions. So in terms of linear size, the central black hole is 10 millions, more than 10 million times smaller than the galactic bulge. And also in terms of mass, despite the huge amount of mass that can be enclosed into a black hole, the ratio between the mass of the black hole and the galactic bulge is of the order of thousands. So the fact that there's a very strong observational relationship between physical properties of the central, tiny, massive black hole and the whole galactic bulge, which exists on much larger scales, told us that probably a profound mechanism of mutual interaction exists between the central black hole and the host galaxy. How do we observe black holes? We observe black holes actually using X-rays. So let me try to explain you how and why. This is an image taken with the Chandra X-ray satellite, and this is an X-ray image which covers an area which is smaller than our full moon as seen in the sky, and each point source is a supermassive black hole. And this image alone contains more or less 5,000 supermassive black holes which are actively accreting. So think about it, if you look at the sky, okay, if you could have X-ray eyes and you look at the sky, behind every full moon equivalent area of the sky, there will be 5,000 active black holes. So our universe is quite full of black holes. We use X-rays to study black holes. In a second, I will explain you physically why we use X-rays, but now technologically, we need to focus these very energetic photons, so X-ray photons, and no standard technique, let's say no technique used, for example, to detect optical photon can help you detecting the X-ray photons. So what we need to perform X-ray astronomy is the grazing incidence. So is a structure of mirrors which have a double geometry, a paraboloid and an hyperboloid, and they are nested, they are concatenated and nested together. And when the high energy photon, X-ray photon, arrives in the telescope, doesn't arrive like in a classical telescope perpendicularly or almost perpendicularly, but arrives at a very small angle, almost grazing the surface of the mirror. This allows to focus these high energy photons and not to lose them inside your detector, basically. And so at the end, to focus X-ray photons, you need very long structures. So this is why the focal length of an X-ray telescope is a fundamental parameter. In this plot, in this scheme in the left, you can see the scheme of the focal length of the ESA satellite XMM-Newton, which is the largest X-ray telescope ever flown. And in the right, you can see an image of its mirrors. So in the right, the image is the image of an X-ray telescope mirrors. In this case, are 58 mirrors nested one into each other, and the photons enter in the interstice between each couple of mirrors, and then gets focused 7.5 meters away, where there is your detector, and then your X-ray photon can be detected, can be registered. This is a collection of images of X-ray satellites which are operating these days. So most of them are very long. So they need to be very long in order to register X-rays. The higher is the energy of the photons that they are able to detect. So you can see XMM-Newton, which I just mentioned, is a European satellite, which has the largest effective area, the largest telescope in X-rays ever flown. Chandra is like the cousin, from the United States, which is comparable to XMM-Newton. It's much smaller, but it has much better eyesight, how to say. We have the Swift Observatory, which is a smaller telescope, but very rapid in changing pointings between cosmic sources. We have AstroSat, which is a recently launched satellite by the Indians. We have NuStar, which is a good example of a very long, actually the longest so far, X-ray telescope, which has 10 meters focal length. So it's very big machine. And we have also NICER, which is a different concept of X-ray telescope, which is it's like a washing machine, more or less. Looks like a washing machine. It's at the top of this image, is on board of the International Space Station. So this is another concept of X-ray telescope, but very interesting nowadays, much lighter. And in the center of the slide, you can see Spectra RG, which is the latest arrival in our skies, in orbit around the Earth. This is an X-ray telescope, half fraction, which has on board now the largest survey telescope with X-rays that we have, which is Rosita, and which just gave us the most detailed X-ray map of our universe just a few days ago. So this is our sky as seen in X-rays. So this is an image by the Rosita satellite on board the SRG. In the horizontal, in the center of the image, you can see an horizontal line, which is our Milky Way galaxy. And many sources. Some of them are extended, but most of them are little points, so are point sources and result. And most of the sources in this image are holes, supermassive black holes. To give you an idea of the improvement of the sensitivity to X-ray observations that we got with this new satellite just launched, let's compare this image of our X-ray sky with the best image that we had before this launch, which is this one, taken by the German satellite Rosat in the 90s. So this was the best X-ray image of the sky that we had, to be compared to the preliminary actual results of Rosita, because during its lifespan, this image will become even deeper and even more detailed. So X-rays allows us to study supermassive black holes. And this is an example of an image of the detector on board XMM-Newton. So it's a series of CCD cameras arranged in an array, 6 above, 6 below, and then you have each little point in the image is an X-ray photon. So you can study and detect different sources within a single observation if you have a field of view large enough. The color of your image is arbitrary, so we are observing X-rays, so we can color what we observe as we want, as we have no idea what is the color of X-rays with our human eyes. But what is the greatest thing about X-rays and X-ray astronomy is that you get to meet every single photon. So the typical count rates of cosmic source in X-rays are not that high, are not that large. And this means that you can follow the photons arriving in your detector. This means that for every photon that you receive from the cosmos, you can say where it arrives in your detector, and you can say when it arrived, and you can say which kind of energy it was carrying. And this means that within a single observation with X-rays, you can easily extract images, like in this case. You can extract light curves or time series. So how many X-ray photons arrive as a function of time, or you can generate spectra. So how many photons of a certain energy arrived as a function of that energy. But how is that we can observe black holes in X-rays? So as I told you, black holes by definition don't emit any kind of light. But what happens is that with X-rays, we actually observe matter very, very close to black holes. Actually, the matter which can arrive the closest to the black holes shines in X-rays. So what happens is that when a black hole hits matter, so matter starts falling toward the gravitational potential well of the black hole, the configuration of the matter forms a disk. So matter starts spiraling in toward the black hole and gets hotter and hotter until reaching temperature of millions degrees. And this means that matter which accretes onto black holes, so matter which is falling onto black holes, can easily emit in X-rays. Now, what happens physically is that the largest is your black hole, the colder is your disk of matter around the black hole itself. So for small black holes, like for example, black holes with a mass comparable to the mass of our sun, you will have very hot disks of matter, disks which typically shine in X-rays. While for supermassive black holes, so black holes of millions of billions times the mass of the sun, you would have a much colder disk. So a disk whose emission would not be in X-rays, but would be rather in the ultraviolet band or even in the optical band. So again, how is that we can observe supermassive black holes in X-rays. The idea is that there is a source of very hot electrons very close to the central supermassive black holes. And this is an artist's view of what we imagine is this hot distribution of electrons. With hot, I mean hundreds of millions of kelvins. So hot and much hotter than the matter of the accretion disk to be able to Compton upscatter the emission of the disk. So the idea is that around supermassive black holes, you have an accretion disk which emits in optical or ultraviolet light, and then a compact X-ray corona, very hot, which Compton upscatters these ultraviolet optical photons up to X-ray wavelengths. And this is how we can observe supermassive in X-rays. Now, this is the image, the most detailed simulation according to general relativity of how does an accretion disk around the supermassive black hole look like in reality. So in reality, the effect of general relativity around the supermassive black hole are so strong that the configuration of matter as we know it doesn't exist anymore, and especially is not visible by us in the same way anymore. And this is very fascinating because not only the general relativity effects can be tested, but it really gives the human mind an expansion of the imagination based on real facts, which is to me quite amazing. This is a simulation of what you would observe if you could travel above the disk. So you're now on the side of the disk, and the effects of general relativity are very strong. Now you're moving above the disk and you observe the disk as it was Newtonian, and then you go below the disk, and general relativity effects again allows you to observe things which are on the other side of the black hole. So this is an effect of the distortion of space-time. So you can imagine that the accretion disk without general relativity would just be observed like a ring, like when you observe it as above, but because of the huge general relativistic effects, this images is completely deformed in this complex configuration. So using X-ray photons, what we do, we register photons coming from these regions. So these space-time regions very, very close to the central supermassive black holes in distant galaxies. This should allow me to finally introduce you to the story of the discovery of X-ray quasi-periodic eruptions, which are signals gathered originating very close to the supermassive black hole, in the accretion disk to the supermassive black hole, and were discovered by the ESA satellite XMM-Newton. So the story starts in the South Galactic Pole. This is an image of the South Galactic Pole, and you can see many, many stars, some galaxies. And there is this galaxy whose name is GSN 069, is 250 million light years from Earth. And it was quite a boring galaxy, non-detected in X-rays, quite average, as many thousands of galaxies in the universe until 2010. In 2010, the ESA XMM-Newton satellite was moving from observing an object to observing another object. And during this time of moving between observations, detected a huge number of X-ray photons originating from the position in the sky of this galaxy. So this is the XMM-Newton SLU program, which is created and led by Richard Saxton. So this is the flux that was detected in 2010. Immediately, astronomers started to be extremely interested in this galaxy because a factor of 200 or more difference in X-ray flux is not something that happens every day. And so Giovanni and Richard started to study this galaxy. Many satellites started to monitor it in X-rays, and its X-ray flux was decaying with time, which is consistent with the hypothesis that a star probably was disrupted by the black hole of this galaxy. But the most interesting results came from pointed observations with the largest satellites, so XMM-Newton and Chandra, which were performed between 2010 and 2019. So I will tell you what happened in these 5 observations. So this is an X-ray light curve taken in December 2010. So the first observation of XMM-Newton just after the discovery in X-rays of this galaxy. So this is a graphic when you can see the number of X-ray photons as a function of time. And it's very difficult to interpret this kind of graphic. How to say it? It's difficult to give a meaning. Just to example, these are example of light curves of another black hole. So a typical supermassive black hole varies in time like this. In a very unpredictable way, I actually spent several months of my life trying to understand these signals, but it was not easy at all. So there are variations up and down, huge variations in short time sometimes, but sometimes not. They are really, really hard to interpret from a human mind point of view. But GSN 069 looked like this again in 2010, but in 2014 looked already different, meaning its signal was very flat. But the most surprising signal arrived 4 years later. So at the end of 2018, XMM-Newton was observing again this galaxy, and Giovanni got the data, and what he observed was something that humans had never observed before. So it was this kind of signal. It was an extremely coherent signal. There were 2 huge flares, 2 huge bursts of emission, which lasted about 1 hour and were separated by 9 hours. This was something that was never observed before. So we immediately went to ask for more observing time with X. And the director gave us 1 full orbit of observation, which is about 2 days. And this is what we observed. So we observed 4 huge spikes of X-ray emission. Each one of them was lasting about 1 hour, and they were repeating very regularly every about 9 hours. So this is a video made of real X-ray images taken by XMM-Newton. And in the bottom, you can see the evolving time series. It's been extremely accelerated. So the whole duration of this movie is about 2 days. But we were amazed. So quasi-periodic eruptions of X-rays were discovered. They were confirmed also by the Chandra satellite, which is in February 2019 observed the galaxy again. Let me skip this. There was a nice press release by the NASA, but you're running late already. Let me just tell you which are the basic properties of the QPs. So the source, the galaxy in X-rays, looks like this. If we neglect the presence of the QPs, it looks like a disk, so the emission from a disk around a supermassive black hole, and then very, very little classical X-ray emission. But then if we look at the QPs, so what happens during this burst of emission, we can see that during the QPs, this disk component smoothly gets hotter. So you can see the evolution in time. Before the QP, the spectrum is the red one. And then during the evolution of the QP, the spectrum goes from red to yellow to green to blue. And then after the QP, the spectrum again goes back from blue to green to yellow to red. So from this plot, we understood that QPEs are very smooth and very short-lived oscillations between 2 phases of the matter, which is close to the supermassive black hole. One phase which is colder, of about 50 electron volt, and a much hotter phase of about 120 electron volt. In the meanwhile, we observed that the supermassive black hole with radio photons, but no strong variability was detected in association with the X-ray one. This is a summary of the properties that we were able to about these QPs in GS069, but let me quickly show you the next result. So where to look next? We have been looking for QPs in other cosmic sources, of course, just to say, okay, is this something which happens often or not? And we found another candidate in the literature, and it was RX J1301.9, which is this galaxy. in the outskirts of the Coma cluster of galaxies. And in this case, this source was already detected in the 80s in X-rays, so it was a known source. We became interested in it because in the literature, we found very interesting time series of this source. So already in the 90s, there were some interesting variability activity registered by ROSAT, but it was in the years 2000 and 2009 when XMM-Newton and Chandra observed it, that time series that were really looking like X-ray QPs were evident in the data. So we asked the XMM-Newton Science Operations Center to perform rapidly a new observation because the visibility window was closing, and this is what we observed. So we observed in 2019 3 strong quasi-periodic eruptions in the nucleus of the second galaxy. This allowed us to assess that this is not like a phenomenon detected by chance, like superposition of a foreground source, but this is something intrinsic to these distant galaxies. So it's a genuine extragalactic phenomenon associated to supermassive black hole accretion. The properties of the QPs in the 2 galaxies are extremely similar, but there are important differences. First of all, the QPs in the second galaxy are much shorter, so they last only about half an hour, and they repeat more frequently. So the time separation between them is much shorter than in GSM 069 when it was about 9 hours. And especially the time separation, the pattern of recurrence is absolutely not clear in this case. So it's not clear if after the little separation between QPs, there would be another big separation or not. And to answer this question, we have a new observation with XMM-Newton, which was just performed, and we're waiting for the results. I will skip this because just tell that the properties of these QPs are very similar between the 2 galaxies. So we are now basically sure that we are observing extragalactic phenomena. What is the interpretation, the physical interpretation? We don't know. Quick answer, we don't know. We're working hard on many different fronts, but the phenomenon is so new that much more work it will be needed. There are a few ideas which sound reasonable, but none of them so far can fit in a quantitative way the observation that we got. There was a paper already this year, so astronomers are starting imagining new possible scenarios in order to explain this new kind of observation. I want you to show this example. So this is an example of a movie made by NASA on a paper which was a theoretical paper, a theory paper, where the author tried to interpret this result. So the idea is that a massive star, a red giant, passed very, very close to the black hole in GSM 069, but didn't get destroyed completely. So it left behind a white dwarf. And this white dwarf nucleus is orbiting the supermassive black hole of GSM 069 every about 9 hours. And for 1 hour, it stays close enough to emit these huge flares of X-rays. Now, I will leave you with this image, which is the image of the orbit, of the possible orbit of this white dwarf nucleus around the supermassive black hole in the galaxy of GSM 069, and that every 9 hours is giving these huge flares. And now, is this the actual physical explanation for this phenomenon? Probably not, but I find it extremely fascinating that there is this interplay between the universe and us. So signals coming from the universe, completely new signals, stimulate the human mind to generate new kind of scenarios in order to interpret these signals. And so thank you very much for listening to this story, and let's see in the future if I can keep on telling you what we will discover and understand, because for sure there is much, much more to both understand and to discover out there. And I will stop here. I will take questions, if any.
Thank you, Margherita. Thank you very much for this very nice presentation. And then we can start with the questions. So if you don't have any microphone, you can also write your questions on the chat, and then I can make the questions for you. No questions? Okay, so maybe I can start. So I was trying to make the connection with our own galaxy and with the galactic center of the Milky Way. And then I was wondering whether, because in the Milky Way, so there are also these Fermi bubbles and the recently detected radio lobes by Meerkat. You mentioned at the beginning that the black hole is quite quiescent. Sagittarius A star is quite quiescent at the moment. But then I was wondering how you connect this AGN activity that you see in X-rays with these features that we see towards the center of our galaxy.
Yes, thank you very much. This is a fascinating question. So I put here the image of the X-ray sky again, because in this image we can see actually the Fermi bubbles that you mentioned. So there are these huge structures above and below the galactic plane, and these are highly energetic particles. And what we think is that these are actually the remnants of past activity of our supermassive black hole. So what happens is that accretion onto black holes, we think, is not continuous forever. It's something that happens, but it's something that has a duration. So accretion can be prolonged when galaxies merge, fine. But when galaxies don't merge, so when black hole hits star by star, this accretion will be episodic. So you will have episodes of activity when the black hole is hitting stars, and episodes of quiescence. So what we think is that in the Fermi bubbles, in our case, are the result of an accretion activity of a few 10 million years ago, a few million years ago, where our black hole was way more active than today, and possibly was an AGN in that case, an active galactic nucleus, and it released a huge amount of material like radio jets on the polar axis, and this created what we observe today as remnants, as Fermi bubbles, so as this huge structure. So our galaxy would be like a young AGN, which is not that active right now.
Thanks. And then regarding the radio bubbles, so the radio bubbles detected by Meerkat, because I think they were suggesting in I think it was a Nature paper, that these radio bubbles were produced by the star formation activity rather than the AGN activity. Is that settled, or is it still under debate?
Settled is probably a too big word, but it's probably very likely that most of the radio emission can be explained by strong star formation and supernovae. Because yes, the structure that we see in radio wavelengths can be easily explained by strong star formation, strong past episodes of star formation. On the contrary, to explain the much higher energy particles that we observe in the Fermi bubbles or in these X-ray bubbles images, you need to rely on the activity of a black hole and not just on stars.
Right. Okay, thanks so much. So we have two more questions. The first one is by Oscar Gutierrez, who asks, is there any new X-ray mission foreseen in the following years to improve the data coming from active nuclei?
Oh, yes, there is. So there are two main X-ray missions that the community is eagerly waiting. So the one that we are all waiting for is Athena, so the Advanced Telescope for High Energy Astrophysics, which is the next European Space Agency large mission. And it should be launched 2030 something. This is the latest. So maybe 10 years to go, but this will be like the revolutionary improvement that we are waiting for. In the meanwhile, much earlier than 10 years, so we have to wait another couple of years to have XRISM, which will be the successor of Hitomi, the Japanese satellite which was lost in 2016. And these two telescopes, so XRISM and Athena, they will have on board a new technology to detect X-rays based on cryogenics instead than on grazing incidence. So these two machines are really what we are waiting for to improve our understanding of active galactic nuclei in the near future in a fundamental way. So these are the expectations. So bright X-ray future.
Great. And then there's another question by Luis Colina. This is the first time that you have detected this phenomenon in supermassive black holes, but quasi-periodic eruptions have been observed in stellar black holes. So could you get any idea of the physical mechanism behind these eruptions from the stellar analogs?
Yes, indeed. Well, when we first saw this a new kind of signal, we immediately thought to smaller black holes. So stellar mass black holes often present very regularly periodic eruptions of X-rays, and we think are due to instabilities of the inner accretion flow close to these stellar mass black holes. But when we took the time scales that we expect from this kind of physical process, we find out that these processes should happen on years or tens of years time scales instead of hours. So either the inner accretion flow around supermassive black hole is significantly different from a thin accretion disk, or this is not the physical mechanism responsible for these eruptions, one of the two. But definitely the comparison between the two is striking, together with their differences.
Mm-hmm. Thank you. And then there's one last question from Bruno Rodriguez, who asks, what would be the optimal observational strategy to increase the number of detections of quasi-periodic eruptions in all the galaxies?
Very nice question. Okay, if I can dream, I dream of a very large effective area telescope, but with a soft X-ray telescope, so very sensitive, between 200 electron volt and 2 kilo electron volt, let's say, huge, which is monitoring the sky like eROSITA more or less is doing, but softer energies. It's monitoring the sky continuously with a detector for transients. So like a transient alert. So on all sky monitoring in the soft X-ray band, but this is a dream at the moment.
Nice dream. Okay, thank you. Yeah, Giovanni wants to add something. Yes, please. You just have to.
No, just to complete this answer. How did we get the second source? I mean, because these two sources don't have just QPEs. They have very similar characteristics from the optical to the X-rays, and very peculiar ones. So the shape of the spectrum in the X-rays, the properties of the emission lines in the optical, the type of galaxy. There are striking analogies that make these two sources rather peculiar among the population of active black holes. So I think that looking for other examples of sources that have these peculiar characteristics, even if we never observe them in the X-rays, or we just have a clue of the spectral shape from just count rates without having a good spectrum or a good light curve, could give us some candidates to then look up with some better satellite in the X-rays, and to look for signatures in the light curve. So I mean, there is hope besides X-rays to identify a few more candidates of this type. And the other thing that I just wanted to mention is that the oscillations that you see in stellar mass black holes are actually very different from these ones, in the sense that we call these things that we observed quasi-periodic eruptions, while in stellar black holes you call them oscillations, because they are really oscillations. I mean, they are very sinusoidal.
No, Giovanni, but I was thinking about the hard eruptions in a GRS, etc.
Yes, but this
was thinking.
True, but this is just one case, one source. So yeah, I don't know if.
I think that was the analogy, not the.
But anyway, that's all.
Thanks.
Okay, I think Luis Colina has a following up question. Do you know if quasi-periodic eruptions are stable over years, or are they very transient?
We know that in this second source, we observed them for at least 18.5 18 years, let's say. So we observe them for sure. Now we're confident in year 2000 and in 2019. Then what happens in between? There are strong hints that in 1994, 91, Rosat was already observing it. And there are also hints that Chandra in 2009 detected something similar to QPs, but in an extremely short exposure. Looks like that they are stable on human timescales, I would say so.
Mm-hmm. And then following up on what Giovanni said, so by identifying these objects with similar characteristics to the AGNs or to the galaxies that you have identified so far, so how many candidates do you have?
Not many so far.
Mm-hmm.
Less than 4.
Okay, thank you very much. So thanks a lot for this very nice and interesting talk, Margherita. I really enjoyed it. And thank you very much to everyone for coming today. And we'll see you after the summer, and hopefully with many more interesting talks. Así que muchas gracias. Espero que tengáis un buen verano y que no paséis mucho calor. Nos vemos a finales de septiembre. Así que muchas gracias, Margherita.
Gracias a ti.
Gracias.
Bueno, hasta luego. Muchas gracias.